CD doesn't know.
The CD? It won't recognize the CD command. Or not, will do. Yeah, it will. It doesn't recognize my copy of those.
You're good?
Install it.
All right, so this is a good stage to transfer this PDB file that you just created and bring these files onto your computer and look at them using VMD. Okay? So that's what I'm going to do. And look for that.
Just use a normal computer. Just trust.
There's so much software on this machine. Open.
This is the cluster directory. Access. You're searching the cluster directory. Yes.
Did you can access this directory? Like that's for
Right.
the
Yeah.
Okay. See what it did? That's what it's a lot of water going. That's 555 using the cubic blocks. Okay? Okay, that's your protein in the middle of the box, and you have an excess. Not enough. This is a small box. Any questions? Yes.
Could you get to the PS FTP thing?
Huh? How did I do that?
You get.
Yeah, the same thing that we did. Upload the file on there. What is that? All programs. You go to funny, and this is PSFTP. Right? So you go to PSFTP. It gives you instructions there. No hostname specifies. Use open hostname. So open sd.rc.usf.edu. Okay? Exactly what we did last time, we changed the property directories into LCDC. Local directory, you also change it to the directory on the cluster and transfer the file and comes to your desktop. Okay? Yes.
I just have one more. How you rename the file with the proxy?
Rename the file with?
Yeah, with the model run file, we
Yeah.
have renamed it.
Right?
Yeah, you just
Which
copy it.
command we have used to rename?
Yeah,
Right.
so use model, copy model1.pdb to some new file.
Yeah, we have copied it.
Yeah.
After that, we didn't change anything.
No, we changed it. We ran the script, right? SH,
Right?
the shell script. No?
It's like, it's not,
That's where
this
that's
is
where
dot
you
backslash.
That's what we did. Okay. Okay. So now we have the protein. We have the protein inside the box in the center with water around it. Okay. Normally at this point, what you want to do is you want to open this topol.top file. Okay. And this topol.top file only has the topology for the protein. It doesn't specify anything about the water. Okay. And how to add water in there? You open this file in VI. Okay.
You open the default.top.
Yeah. You do VI topol.top. Okay. What you want to do is you want to go at the bottom of this file. And if you keep scrolling down, it's going to take you forever. It's a really long file. Okay. So what I do is I search for certain things. Okay. I go search for, and you want to search, you just put a slash. Okay. So that takes you to the search mode. Okay. And so if you want to search anything in there like bonds, it will take you to bonds. Okay. You search for dihedrals, takes you to dihedrals. Okay, so it's basically going down the file. Okay. And then I'm going to search for hash. That takes me pretty much to the bottom of the file. So this is pretty much the bottom of the file. Okay, there's lots of stuff in there that you don't need to worry about at this point. Okay, all you do is go down in there and look at what's inside molecules. Okay, so at present there is only one molecule in there, that is protein chain A, and number of molecules is 1. Okay, so we're going to go down in here and insert, and I'm going to put the name. So this is basically the name of this protein chain A. Okay, that's what is in the topology on top. Now you want to put the name of the water molecule. Okay, so, and how many did we have? You remember?
16.
3,000
wait, yeah, sorry.
something. We can go back and look. So you can escape out from there. We have 3,926. But how do I know I can call them solves? The reason I can call them solve is because if you look at the bottom of this model 1 file, see all these residues are named as solves here. Okay? The 3926. Right here, we're going to add. Okay, there is a protein chain A, and then you have 3926 solvent compounds. Alright, so now your topology file has this information. So at this point, your topology file is updated with information that you need to also account for the water molecules. Okay. At this point, you want to add some ions. in your solvent, right? Let's do the ions part a little later, maybe in the next lecture. Let's try to run this simulation without any ions. Okay. The way you want to add ions is, you know how many waters you have, right? You have 3926 waters in the box. You normally want a certain concentration of ions. Okay. You want say 100. You want say 50 millimolar of sodium chloride, or 50 millimolar of potassium chloride. Okay. So how do you know how many waters you need to replace in order to? So what you do is you take out certain waters, and instead of those waters, you put ions in there. There's a code that does that. But you need to know how many waters to replace with ions. So if you want a 50 millimolar concentration, you have 3,926 waters. How many waters are you going to replace with ions? So one of the things you should remember is that about 55 moles of water, okay, in 1 liter, right? Those many moles of water. So if you want 1 molar concentration, 1 out of every 55 waters has to be replaced. Then you get 1 mole of concentration. If you want 100 millimolar concentration, you replace 1 every 550. If you want 50 millimolar, you replace 1 every 1,100. Right? So if you have 3,926, you roughly need, for a 50 millimolar concentration, you roughly need about 3 of each ions, or 4 of each ions of sodium and chloride. Okay. Now this is a homework question that I have posted on myself, posted homework 3. So this is something I want you to think about how you're going to do this. It's just a simple, mathematical problem, right? You have so many waters, you want this concentration of salt, how much salt are you going to put inside it? So once you have had the chance to go through that homework, you will do it in the next time. Okay, so something you need to think about. And it's a very basic arithmetic. Okay, so we're going to now, we have this ready, and we have this topology file. What else do you need to run a molecular dynamics simulation? You need an initial set of conditions. Okay, and what temperature do you need to run it at? What pressure do you need to run? What other variables do you need? Okay, so all these variables I have placed in the shares folder. Okay, when you go to see these shares. Those variables you supply in terms of a file that ends with MDP. Okay, so MDP is essentially short for molecular dynamics parameters. Okay, so what does this file look like? If I go to EM or 0 to 100 nanoseconds or MDP, that's what this file looks like. Okay, this is all the information there. That's the title. You can give it any title you want. Okay. You can leave this line as is. Okay, this tells you where the CPP processing, where the CPP is located. Your integrator, in this case, is equal to NB, but integrator could also be stochastic dynamics or Brownian dynamics, because GROMACS allows you to do many different things. Okay, so the integrator here is NB. Your starting time step, which is T init, is 0. Okay, dt is your time step. And the time step is, everything is in picoseconds, right? So this is 2 femtoseconds. Like we discussed, what time step you need to choose, it's around 2 femtoseconds. Okay? So this is your dt time steps. And how many steps do you want to run? So if you want 100 nanoseconds of data, and this is your time step, these are the number of steps you want to run. Right? What is that number? 50 million steps. So you want to do this thing 50 million times to get 100 nanoseconds. Okay? So I've broken these input into different things. Okay? So the first is the very general input, how long do you want to run this simulation? Okay? And then anything that follows a semicolon is basically a comment. Okay, so all these 3 lines are comments. You can, for your own information, if you want to put stuff in there, you can just use a semicolon and put any comment in there. Okay. The next 3 lines are essentially constraints. Okay. What we are doing in these simulations is we are constraining all the bonds. Okay. That is, you're not letting the bond have a harmonic potential. You're just constraining its length because you're not interested in bond vibrations. If you're interested in bond vibrations, then this time step has to be much smaller because bond vibrations offer of the order of 1/10 of a second. So if you're not interested in bond vibrations, you choose a larger time step and you constrain the bonds. Okay. And the next 2 are more details that I'm not going to go through, but the way you're constraining this is linear dump mode and some more algorithmic details. Okay, and then you have to say what is going to be the output of this MD simulation. Okay? NXT X out tells you NXT V out and NXT F out are basically coordinates, velocities, and forces. Okay, and when you write these 3 lines in here, it's going to create a file which is going to have an extension of .trr. That is going to be a dot trajectory file. And that trajectory file is going to have all the information on coordinates, velocities, and forces. Okay, and what I'm doing here is I'm saying you want to dump all this stuff. You don't want to dump the forces at all. The velocities and coordinates you want to dump every 500,000 steps. That is every nanosecond. Okay. Now, if you want, if you run this for 100 nanoseconds, you're going to have 100 frames where you have both coordinates and velocities simultaneously. Okay. And in addition to that, you have this command here, NST XTC out. And what this command is going to do is going to generate a .xtc file. And that will only have coordinates, okay, not velocities. And that I am dumping every 10,000 steps or every 20 picoseconds. Okay? Right? So it's going to, right now it's going to generate one file, which is the TRR file. It's going to generate a second file called the XTC file. That only has coordinates. TRR has both coordinates and velocities and forces if you want. Okay? And so we're not interested in the velocities at this point, but I'm still dumping them every nanosecond. And the reason is if your job dies for some reason or gets killed because of some reason, you always need the set of velocities, right, to restart. So you'll always have the previous nanosecond where you have velocity saved so you can extend the trajectory. Okay? Yeah? All right. And then you have NST log. Okay? So NST log is going to create another file called the .log file. And that .log file is going to have a lot of information that we're going to look at. And it's going to dump information every 1,000 steps. Okay? And NST energy creates a 4th file. Okay, so this is 1, 2, 3, and 4. This will have a lot of information about all the energetics. What is the energies of the bonds? What are the energies of the dihedrals, angles, potential energy, kinetic energy, lattice energy, pressure, temperature? Everything is going to be, anything related to the Hamiltonian is going to go in there. So as you run the simulation, you can have a lot of data, not only on coordinates, but also on the energetics of the simulation. Okay, that is just the output control. Okay? So the more frequently you dump coordinates, the bigger the file gets. So you want sort of a constraint. Okay? So when you have really big systems and you want to run them for a long time, you don't want to save very often, or you'll end up with terabytes of data very easily. Okay? The next one is this neighbor searching and electrostatics. Okay? This section you should not change unless you are confident of what you're doing. Okay. The first line says here is PBC. PBC is short for periodic boundary conditions. Okay. So we are applying periodic boundary conditions along X, Y, and Z axis. Okay. But you can choose whether to do just X, just Y, and Z. If there's no reason, we are applying periodic boundary conditions in all dimensions. Okay. This I'm going to leave out. Okay. And I'm not going to explain what MST list is at this point. But if you're interested, I can discuss all these separately in office hours as to what they mean. Okay. The part here is you have this R Coulomb. Okay, which is the radius for Coulombic interactions. Okay, and that is set to 1. So if it's a radius, it is in length, right? So 1 is basically nanometers. Okay, so there is a radius to do Coulomb interactions up to 1 nanometers. Okay. Now what does that mean? It means you're going to do so for all the atoms which are within 1 nanometers of a given atom, you're going to calculate the electrostatics explicitly or the Coulombic interactions explicitly. But beyond 1 nanometers, you're not going to calculate it explicitly. Because what you really want to do is you want to calculate all the way up to infinity. That is why you're doing these periodic boundary conditions. But if you try to sum everything up to infinity, you can't. Right? So the first 10 angstroms, where the interactions are the strongest, you're doing the Coulombic pairwise interaction. Okay? But beyond 10 angstroms, what you're doing is you're using PME or Ewald summation. Okay, so you take the space, take a Fourier transform it, see where the patterns are, and just sum up the patterns. Okay, so up to 10 angstroms exact. After that, it's slightly approximate. Okay, and that's what this R Coulomb means. Okay, and all the stuff here, this is Fourier spacing, PME grid, Ewald, RTOL, optimize FFT, is all related to this Ewald summation in the Fourier space. Okay. And then comes this, so this allows you up to this point, what you're doing is you have a periodic boundary condition, okay, and inside that periodic boundary condition, up to 10 angstroms from each atom, you're summing up electrostatics exactly. Beyond 10 angstroms, you're using Ewald summation. Okay, it's a slightly approximate solution, but it's much faster. Okay? And so, there's a little story here about Fourier transform. So everything is Fourier transform. So this was back in the 90s when people were trying to develop faster and faster Fourier transform algorithms. So you should be able to do a Fourier transform and sum everything up in Fourier space. And the faster the algorithm got, people were like, oh, I got something better. I got something better. But after a certain point, this algorithm stopped advancing because you're like, you can't do anything faster than this. Okay? So the very last one that came out of Fourier transforming, which was sort of a breakthrough in how do you do Fourier transform, came out from this guy's lab, I forget his name, starts with J, from MIT, and he called it FFT.2. Okay, FFT is it's not fast Fourier transform. It's fastest Fourier transform in the West. It's cool. So every time you see, any molecular dynamics, you're going to see everyone using FFT.2. That's fastest Fourier transform in the West. That's so cool. Mathematicians can be funny. Don't tell them. Okay, so this is up to electrostatics. Then you have this van der Waals summation. So van der Waals, as you see, as you go further and further away, if you remember that curve, the van der Waals potential becomes very, very tiny. Okay, the contributions of van der Waals interactions become much, much smaller. So you can use the van der Waals type, which is also a cutoff, and you can have a cutoff radius of say 1 nanometers. Okay. Now in the homework, there's a problem on this. Okay. So there's you will see that in the homework I have given you a numerical problem where you're given an electrostatic calculation. If you make a cutoff of 10 angstroms or 12 angstroms, you get a certain energy. Okay? And if you don't make a cutoff, you get a different energy. So what is the sort of contribution beyond 10 angstroms? So you get a certain error if you're doing cutoffs for electrostatics. And you get a similar error if you do cutoffs for van der Waals. And you'll see that the error is very, very, very tiny beyond 10 angstroms. But electrostatics, you'll find a very large error. Okay, so you can do that mathematically and you see it. Just plug in the numbers in the equations and you get it. Okay. All right. Then we have this temperature coupling stuff. Okay. You want to couple the temperature using, in this case, a velocity rescaling algorithm. That is V rescale. PC group means what is the temperature coupling group. So in this case, the entire system, which is protein plus water, is coupled at the same temperature and back. Okay, it's got one single regulator. But if you're, but sometimes what you can do is you can, if you're running a very large protein, you can couple the protein to one temperature and the bath to a different temperature. So it gives you the flexibility to define these groups and put different temperatures for different groups. So as an example, we were running a simulation of a lipid bilayer which was on top of a support, okay? And the support was an artificial support. And so we didn't want the support to move much, so we coupled the support to 5 Kelvin temperature, and everything else was 310 Kelvin. So if it's at 5 Kelvin, it's really not going to move, right? It's like pretty much frozen. So it gives you the advantage to do these hypothetical simulations. Okay? That's, in this case, the reference temperature right now is 298, so you can change it to whatever you want. And this is in Kelvin, okay? And LBC, so like I said, when you are trying to assign the initial set of velocities, you assign them based on a Maxwell-Boltzmann distribution. So it takes the seed, a random seed value. If you set it to -1, the seed number that it chooses is essentially nothing but the processor ID itself. Okay, that's the random seed. Okay, and then you have pressure coupling. So the pressure coupling is done here using this algorithm, Parinello-Raman algorithm. And the pressure coupling type is isotropic. That means you have same pressure on all faces. So isotropic means you can also choose anisotropic, and in that case you can define all the components of the pressure separately. Okay. This is the reference pressure, which is in bar. That's the unit. So it's 1.01325 bar, which is equal to 1 atmosphere. Okay. And this is the tau p. You remember I talked about how slowly or how fast you need to change the pressure. There was P minus P0 1 over tau relationship. That is, tau dictates how fast you need to change the pressure. You calculate the instantaneous pressure, and you have the pressure you want to set at. So you want to change the pressure slowly or very fast. So this tau is basically how fast you want to do it. So this is basically 1 picosecond. So within 1 picosecond, you want to bring it. So if you find the temperature pressure to be off, you want to give it 1 picosecond before it reaches that level. Okay, and the same thing you have for temperature also. There's a tau T, which is 1 picosecond. So you don't want to change all these things unless they are reason. Okay, and then you have this thing about generating velocities. You want to generate velocities. Since you're going to start from the beginning, you want to generate velocities. So you have a seed, and then you have temperature. Now you know that the temperature is 310 Kelvin, but we're trying to maintain it at 298, which is weird. That shouldn't be the case, right? So I'm going to go and change that. Basically going here. Change this to now it's consistent. Oh, this is read-only. Very nice. How is it read-only? I created it. Okay? No problems. If I created it, I can change its permissions. Oh, I can't even do that. Unbelievable. So go. I don't have sudo permission. No.
Can't you just put an exclamation point at the end of the right bit? And it'll like make a new one or something?
It's like